let's get the actual method defined formally now. The so-called one-sample t-test and the corresponding p-value, which is the name of this. If we begin from the bottom of this method box here, we are now in this box hypothesizing that some mean equals a fixed number, mu0. We just exemplified that this number was 0, but it could be any kind of specific choice that we want to make a hypothesis test about. So mu0 is a given number in the actual use of this. So we have a number mu0. What I do is to compute the difference between the data and the hypothesis. I think it's very common sense. I hypothesize this, I have compute this mean. So of course, if I should say something about whether or not I believe this hypothesis mu0, I should compare with the data. I should compare the data with the hypothesis. Then we have to think about the variability of this comparison. We talked about that last week. This is exactly the same. We standardize this difference between the data and the hypothesis by the standard deviation of the mean itself, right? I call this the observed t-statistic. I call it like that because under the null hypothesis, assuming the null hypothesis, two different ways of saying the same thing, this statistic, as we saw last time, follows a t-distribution. So a t-distribution, which is this version of the standard normal with a little bit heavier tails, sometimes almost exactly the same as the standard normal. This is the distribution we can use to qualify whether I'm close to or far away from the hypothesis, right? If I'm close to the hypothesis with my data, I would tend to say, well, the hypothesis is probably okay. If I'm far away from the hypothesis with my data, I would be inclined to say I don't believe the hypothesis. It's really common sense and no rocket science here, right? Close to, I believe. Far away, I don't believe. How should I make the distinction? Well, we use the probabilities and make the probability to make a distinction between what we think is far away or close to. And this is the t-distribution that will do that for us. So the p-value, if we have, for instance, t-ups here, we have a 0 here, I would have minus t-ups if it was, anyway, if t-ups was positive, otherwise it would be vice versa. It's symmetric. It didn't quite make it like that, but it is symmetric. Then the p-value is the probability. Here, those two together. That's the 2 times because it's symmetric. It's the probability to sort of go beyond the discrepancy that I've seen, right? I've seen 1.67 in the mean, and then I standardize it. And then I ask myself, how likely is it to go to that extreme given the null? And then to be formal about it, we would have to say to go to that extreme or even further away. That's the p-value. The probability to go beyond the observed standardized difference, which is called the observed t-test statistic. That's how to do it. So basically you can see that's a plug-in formula. This is a number you can find in a given context. You have your x, you have your hypothesis, compute the s, find the number, and then you take the t-distribution and find the probability. And then that's the first part of it. Then the second part of it is to make your conclusion based on this p-value. And there is a classical sort of way of looking at p-values that are put in this table. This is also used as a kind of default notation in the way R is providing p-values. It will actually provide a 3-star, sometimes notation here when we have something which is very unlikely, less than 1 out of 1,000, less than 0.1%. We call that a very unlikely event given the null, assuming the null. Or differently put, we would call such a very small p-value a very strong evidence against the null hypothesis, right? So, with a very small p-value, basically we have proved our point. That's what the scientists and whatever are all looking for, aiming for. I've come up with a new idea for a new drug. I'm going to test it. I'm going to do my p-value, and the p-value was 1 out of a mil. Woo-hoo! I got my result. I found it. Nobel, I'm coming. It's significant. Very strong evidence. That's the role of the p-value, right? The very global distinction, if you want to be strict about it, between where do I found, I mean, did I find something or did I not find something? If I allow myself to be this simple-minded, and this is at the core of the global discussion about this whole hypothesis test and p-value procedure, should we allow ourselves to be such unintelligent about the real world that either it's like that or it's not? Maybe it's a continuous thing where we have evidence. We have some evidence against and some evidence pro. But I realize sometimes you need to make a decision. And FDA has to make a decision about which drugs are allowed on the market. And so on. In a company, we have to make a decision about what to do in the society. We need to make decisions about where to send the money. There are decisions to be made. So, of course, sometimes it is a black and white situation, even though we know that the knowledge is not, I mean, really if we think about it, there is no clear yes or no, but I have to do it, either yes or no. Cannot stand still, I have to move either right or left. The global decision limit has, for some odd reason, been set at 1 out of 20, 5%. This is also defaults in all software programs that you'll find. This is the distinction between where we say we found something or where we would have to say I couldn't find anything. Or I have proved something or I didn't prove anything. I found a significant difference, I didn't find a significant difference. That's the 5%. And that's why we say, in a way, between 5 and 1%, we called it some evidence. Above 5, there are weak. Above 10, there are no evidence at all. That's the global sort of interpretation table for p-values. If you see something in the newspaper, this was found significant, typically it's because some p-value turned out to be less than 5%. That's how it goes. And the formal definition, in a way we used it already. Please note, this is in fact a very general table and a very general definition that can be applied to all the situations that you meet in the course, not only the one we've seen now, which is situation 1, but on to all the rest of the situations you will meet in your rest of your life. When talking about hypothesis test and p-values, this is very generic. The p-value is the probability of observing a test statistic which is at least or more extreme as what we actually observed. This is something we have to digest, this definition and the understanding. And I think I mentioned it already last time, or let me repeat it. The world is still digesting, or ruminating, as I heard someone call it. And I'm not sure they will ever get to the final point of this. But we have to do our best. And you are the guys who are going to make sure the world will keep on doing the right thing when you hit the real world after this. You cannot assume the others will do it for you, because not many people understand these concepts really to the bottom of what it's about. The thing is, a p-value is, and probability is difficult. A p-value is actually only kind of a scenario-based probability. It's not in a way, it's not a real probability that we can use for anything. We cannot predict anything in the future by this probability. It's just a scenario-based probability evidence measure, because the probability is computed under some assumptions, and it's a scenario-based. What if the null hypothesis is true? So it's a scenario-based probability that we use just to sort of quantify within our data set what kind of evidence we really have against the null. That's what we can use the p-value for, not to predict the future. And this is where the change sometimes drops off the, whatever it's called in English. Let's get back to the example and see how it works very easily in practice. It's not complicated in practice, this. It's only complicated if you force yourself to really think deeply about what these things really mean. We can easily work with these things without going into the deep abyss of existentialism about what's everything. And my recommendation is don't go there. If you go there, let's meet out there somewhere. But don't go there. You're more happy if you don't go there. If we test this hypothesis, here is the test statistic that you already saw. The observed mean compared to the hypothesized mean for this particular hypothesis, divided by the standard deviation over root n, which is the standard error of the mean, the uncertainty of the mean, this s over root n. I find the number 4.67. I have to use the t-distribution. I have to use r to look up this probability. So I go for 1 minus pt, which is exactly the probability. 1 minus pt is this probability, right? 1 minus pt is the probability of being to the right of 4.67, to be even more extreme than 4.67, and then I multiply by 2, and by this I manage to add up the 1, because a similarly extreme discrepancy could have been to c minus 5 or to the left of minus 4.67. So I compare and I see this small probability. If I forgot how to interpret the p-value, I go back to my table and I would see in this case I'm in this category, right? Smaller than 1% but slightly larger than 1 per mil. So it's a strong evidence against the null hypothesis. That's my conclusion. What does that mean? Do I believe in the null? I don't believe in the null, right? I believe I've proved the null to be wrong when I have this small p-value. It's quite easy to do that in R. Let me show you. Again, I stick to this one here due to the color and the size. It could be done manually by putting in the data into X and measuring the length of X. Just by manual formula handling, compute the t-ops, and then find the p-value as I've already shown you, right? Just straightforward computations. Or, as you've seen already, actually, we could just say, use the function t-test. By default, this function actually tests the hypothesis of being 0. You could test other hypotheses, but this is the default. And that's what we wanted here. So it provides actually, now it only gives with 3 decimal points, but it tells you the p-value. And in fact, it also gives this confidence interval that we learned about last week, right? The confidence interval is away from 0. That's one way of saying it. We do not have the 0 in the confidence interval. Actually, the confidence interval is pretty far away from 0. And this is the link that we'll get to now. That rejecting the null hypothesis, which we've done now, is equivalent to the observation that the confidence interval does not include the null, which is 0 here, right? So having a confidence interval which does not include 0, actually we already performed the hypothesis test in a way, although we didn't get the p-value. This is the analogy. These two things, they come hand in hand. And this is what we should see. I just want to make sure I'm on the right track. Yes, still on the right track. I've done this already, but let's take the words formally again. What we've done now is a hypothesis test. We use the terminology that we reject the null hypothesis if the p-value is small, to say it briefly, right? We can define the level of smallness in different ways. So we allow ourselves to talk generally about a level alpha hypothesis test. That's why I'm saying alpha most often is 5%. The global default choice of alpha is 5%, but to be flexible here, we need to be able to work with other risk levels. Maybe in some context you want to define other risk levels. So we talk about the level alpha, typically 5%. And if the p-value turns out to be smaller than the pre-chosen alpha, given by the contract, by the situation, the alpha is given by the situation, then we say that we have rejected the null hypothesis. We call the alpha sometimes also the significance level. It's the threshold between whether we claim something significant or not. That's the sort of the wording, the terminology. And if not, if we don't reject, then we have a bit of a danger here, but let's do it now. If we don't reject, it would be most safe to just say, I don't reject. But we allow ourselves to use the same word as many other on the globe. We allow ourselves to, instead of saying, I couldn't reject the null, I say that I accept the null. But I would like to warn against this word, because there is a danger to be fooled a little bit about the use of this word. Because accepting something statistically just means that you couldn't reject it, right? It doesn't mean that I proved it right. There's a hell of a difference. Sorry for cursing, but that was a point to be made here. We'll get back to that, of course. And the terminology, I used it already. This is just to teach you how people talk about this. We talk about that we have a statistical significance, an effect, a finding was significant. It's said, if you see it in the papers, means that we have a small p-value that made us reject a null hypothesis. So we have a statistical significance. Again, the word significance, of course, is used in a statistical meaning and not only in the sort of everyday English understanding. Meaning was the word I was looking for, of the word significance. It's a little bit easier if you talk about statistics in Danish. And then in Danish we also say, when we talk statistics, we say significance. I think you understand that Danish word now. But when you say that, you know you're talking stats, because you're not sitting in the bar Friday night and talking about, I think this is a significant, really nice beer I'm having here. At least maybe some of us did, but that was at university, and you know. You should see the guys at university at math and physics departments. So, whoa. But common people don't go around and say in Danish the word significant. So we would know that we were geeking science or stats now and not talking everyday Friday bar language. In English, I think it's a bit more difficult because the word significance is a more common word to use. I shouldn't say. I should move on. So I'm repeating myself, but it's okay to repeat this. With a fixed alpha, we conclude that we reject the null, and we found a significant effect, and that B works better than A. We said this already. Let's have a little. Let me just check. Yes? Here we go. Good job. I'm happy. There's a little trick here. The p-value was 50% here. It was not small. So it was not 5% or smaller. The p-value was pretty large in this example. It was not small. That's why red could not be true. Red would only have been true if we had a very small p-value. We didn't have a small p-value here. It was a pretty large p-value. Good job there with the odd name.